Look at this simulated network topology. As 5G infrastructure expands to support millions of IoT endpoints, customized network slices, and localized edge computing nodes, the data volume multiplying aggressively across the system creates a critical scaling bottleneck. For decades, telecommunications relied on rigid, if-then rules-based automation. Managing the bandwidth allocation and fault detection of these networks required human operators sitting in vast network operation centers to oversee and approve nearly every action. In the 2010s, operators integrated reactive machine learning to analyze historical data and detect anomalies. Yet, while these algorithms could trigger an alert, they still required human engineers to interpret the data and manually execute the remediation. Today, that manual oversight has reached a mathematical limit. The volume of 5G telemetry data, paired with strict sub-50 millisecond reaction times demanded by modern service-level agreements, has permanently outpaced human operational capacity. By 2025, telecommunications requires Agentic AI, autonomous software entities that perceive the network state, formulate decisions, and act without explicit human instruction for each task. This diagram outlines a telecom stack's foundation: the radio access network, the edge, and the core. Operators install an agentic layer atop this topology. Operating on a closed loop, the first stage is perception. Agents constantly ingest live telemetry and sensor data. The second stage is decision. Using learned models, agents evaluate data against predefined objectives to formulate real-time solutions. The final stage is action. Agents autonomously trigger hardware remediations, sending commands back down into the physical layers. Unlike consumer large language models designed to generate text or summarize documents, these telecom agents are engineered to manipulate physical infrastructure states and active data routing. By continuously cycling through perception, decision, and action, control of the network moves at machine speed. Consider a specific operational challenge. Enterprise users within a dedicated urban network slice suddenly report a critical latency spike. This chart details the multi-agent hierarchy designed to handle this. At the very top is the orchestrator agent. It ingests this complex intent, in this case resolve latency in the urban slice, and identifies the root cause of the congestion. Rather than executing the fix itself, the orchestrator breaks this high-level intent down into actionable subtasks. It then assigns those subtasks to specialized execution agents. These agents strictly optimize localized resources within their designated domains. To clear the congestion, a RAN execution agent might adjust localized antenna beam formations, while a separate core execution agent dynamically reroutes background traffic to free up bandwidth. While the execution agents manipulate the hardware, the orchestrator agent continuously monitors their success metrics to confirm that the original latency issue is actually resolved. But responding to latency is still reactive. Predictive agents make up the third category in this hierarchy, analyzing data to forecast physical conditions before any alert is ever triggered. This waveform shows live vibration telemetry ingested from a base station cooling fan. Through continuous monitoring, the predictive agent identifies a microanomaly representing early bearing wear. The agent uses the signature to forecast a complete hardware failure 3 weeks in advance. It then autonomously schedules parts procurement and an engineer dispatch during a low-traffic maintenance window. Replacing the bearing before it breaks results in zero unplanned downtime. The multi-agent hierarchy turns reactive firefighting into proactive orchestration. These AI agents are not isolated proprietary black boxes. To function, they must integrate directly into the established multi-vendor infrastructure of modern telecommunications. This schematic illustrates the 3GPP integration architecture. Here, an execution agent is encapsulated as an RApp on the non-real-time RAN intelligent controller, providing standardized access to network interfaces. From the controller, the RApp issues real-time optimization recommendations to physical base stations. By managing spectrum sensing and beam power allocation at the base station level, the RApp improves the user's quality of experience by clearing radio interference. Deeper in the network stack, at the core and transport layers, agents interface directly with software-defined networking controllers like Open Daylight. In a cybersecurity scenario, a predictive security agent might detect an incoming distributed denial-of-service attack aimed at an enterprise network slice. The agent rapidly commands the SDN controller to reroute the affected traffic, simultaneously scaling up scrubbing virtual network functions to absorb and mitigate the attack. Faster, more urgent speed. This NFV orchestration occurs at machine speed, neutralizing the threat before human operators register the initial alert. Standardized APIs translate these agent calculations into instructions for the physical hardware. What exact algorithmic frameworks allow autonomous software to make these decisions safely? For execution agents responsible for continuous resource allocation, operators rely on reinforcement learning. Before ever reaching the live network, these agents learn optimal policies through intense trial and error inside simulated sandbox environments. This training produces an agent capable of dynamically assigning frequency bands to base stations, constantly maximizing data throughput while minimizing signal interference. Orchestrator agents use a different framework. Because they deal with high-level planning, they utilize large language models integrated with external API tools. This structure allows an orchestrator to ingest a complex natural language request from a human operator, like optimize the network for holiday traffic peaks, and break it down into executable capacity provisioning sequences. Pure LLM architectures are avoided due to operational latency and the risk of hallucinated actions. Operators deploy hybrid systems that rely on reinforcement learning for execution and LLMs for orchestration. Granting autonomous software direct control over infrastructure supporting critical services and millions of users presents an obvious engineering vulnerability. To secure the network, operators implement policy as code. This establishes hard mathematical limits on what an agent is permitted to execute. If an agent attempts to change a configuration that violates a defined risk threshold or falls outside an approved change window, the action is immediately rejected and rolled back to a safe state. Regulators also mandate human-readable audit logs and explainable AI. Operators must be able to prove exactly why an agent took an action to maintain compliance with lawful interception standards. In telecommunications, an autonomous system's capacity to audit and explain its decisions is just as critical as its ability to optimize the physical network. This dashboard illustrates the operational outcome. Agentic AI establishes network infrastructure as an autonomous, self-healing environment. Production deployments at early adopters like AT&T show critical network incident response times dropping from an hour to under 5 minutes. At the hardware level, autonomous RAN optimization yields a 25 to 35% improvement in spectrum efficiency while reducing transmission latency by up to 20 milliseconds. By automating routine labor and forecasting hardware failures through predictive maintenance, operators achieve a 10 to 15% reduction in total operational expenditures. Maintaining 99.99% availability and sub-50 millisecond latency allows operators to provision specialized enterprise slices at price points 5 times higher than standard broadband. For a large operator, automating these on-demand slices generates an estimated $1 to $5 billion in annual revenue.